The Fermi level is the total chemical potential for electrons and is usually denoted by micro or F. The Fermi level of a body is a thermodynamic quantity, and its significance is the thermodynamic work required to add one electron to the body. A precise understanding of the Fermi level, how it relates to electronic band structure in determining electronic properties, how it relates to the voltage and flow of charge in an electronic circuit, is essential to an understanding of solid-state physics. In a band structure picture, the Fermi level can be considered to be a hypothetical energy level of an electron, such that at thermodynamic equilibrium this energy level would have a 50% probability of being occupied at any given time. The Fermi level does not necessarily correspond to an actual energy level, nor does it require the existence of a band structure. Nonetheless, the Fermi level is a precisely defined thermodynamic quantity, and differences in Fermi level can be measured simply with a voltmeter. The Fermi level and voltage. Sometimes it is said that electric currents are driven by differences in electrostatic potential, but this is not exactly true. As a counterexample, multi-material devices such as p-n junctions contain internal electrostatic potential differences at equilibrium, yet without any accompanying net current. If a voltmeter is attached to the junction, one simply measures 0 volts. Clearly, the electrostatic potential is not the only factor influencing the flow of charge in a material. Pauli repulsion, carrier concentration gradients, and thermal effects also play an important role. In fact, the quantity called voltage, as measured in an electronic circuit, has a simple relationship to the chemical potential for electrons. When the leads of a voltmeter are attached to 2 points in a circuit, the displayed voltage is a measure of the total work that can be obtained, per unit charge, by allowing a tiny amount of charge to flow from one point to the other. If a simple wire is connected between 2 points of differing voltage, current will flow from positive to negative voltage, converting the available work into heat. The Fermi level of a body expresses the work required to add an electron to it, or equally the work obtained by removing an electron. Therefore, the observed difference in voltage between 2 points A and B in an electronic circuit is exactly related to the corresponding chemical potential difference in Fermi level by the formula where E is the electron charge. From the above discussion it can be seen that electrons will move from a body of high micro to low micro if a simple path is provided. This flow of electrons will cause the lower micro to increase and likewise cause the higher micro to decrease. Eventually, micro will settle down to the same value in both bodies. This leads to an important fact regarding the equilibrium state of an electronic circuit. An electronic circuit in thermodynamic equilibrium will have a constant Fermi level throughout its connected parts. This also means that the voltage between any 2 points will be 0 at equilibrium. Note that thermodynamic equilibrium here requires that the circuit be internally connected and not contain any batteries or other power sources, nor any variations in temperature, the Fermi level and band structure. Although this single particle picture is an approximation, it greatly simplifies the understanding of electronic behavior and it generally provides correct results when applied correctly. The Fermi-Dirac distribution gives the probability that an electron will occupy a state having energy. Alternatively, it gives the average number of electrons that will occupy that state given the restriction imposed by the Pauli exclusion principle. Here, T is the absolute temperature and K is Boltzmann's constant. If there is a state at the Fermi level, then this state will have a 50% chance of being occupied at any given time. The location of micro within a material's band structure is important in determining the electrical behavior of the material. In an insulator, micro lies within a large band gap, far away from any states that are able to carry current. In a metal, semi-metal or degenerate semiconductor, micro lies within a delocalized band. A large number of states nearby micro are thermally active and readily carry current. In an intrinsic or lightly doped semiconductor, micro is close enough to a band edge that there are a dilute number of thermally excited carriers residing near that band edge. In semiconductors and semi-metals, the position of micro relative to the band structure can usually be controlled to a significant degree by doping or gating. These controls do not change micro, which is fixed by the electrodes, but rather they cause the entire band structure to shift up and down. For further information about the Fermi levels of semiconductors, see SZE. Local conduction band referencing, internal chemical potential, and the parameter zeta if the symbol is used to denote an electron energy level measured relative to the energy of the edge of its enclosing band, C. Then in general we have equals C, and in particular we can define the parameter zeta by referencing the Fermi level to the band edge. It follows that the Fermi-Dirac distribution function can also be written. The band theory of metals was initially developed by Sommerfeld, from 1927 onwards, who paid great attention to the underlying thermodynamics and statistical mechanics. Confusingly, in some contexts the band-referenced quantity zeta may be called the Fermi-level chemical potential, or electrochemical potential, leading to ambiguity with the globally referenced Fermi level. In this article the terms conduction band-referenced Fermi level or internal chemical potential are used to refer to zeta. Zeta is directly related to the number of active charge carriers as well as their typical kinetic energy, and hence it is directly involved in determining the local properties of the material. For this reason it is common to focus on the value of zeta when concentrating on the properties of electrons in a single, homogeneous conductive material. By analogy to the energy states of a free electron, the EF state is the kinetic energy of that state and C is its potential energy. With this in mind, the parameter zeta could also be labeled the Fermi kinetic energy. Unlike micro, the parameter zeta is not a constant at equilibrium, but rather varies from location to location in a material due to variations in C, which is determined by factors such as material quality and impurities, dopants. Near the surface of a semiconductor or semi-metal, zeta can be strongly controlled by externally applied electric fields, as is done in a field effect transistor. In a multiband material, zeta may even take on multiple values in a single location. For example, in a piece of aluminum metal there are two conduction bands crossing the Fermi level. Each band has a different edge energy C and a different value of zeta. The value of zeta at zero temperature is widely known as the Fermi energy, sometimes written zeta zero. Confusingly, the name Fermi energy sometimes is used to refer to zeta at non-zero temperature, the Fermi level and temperature out of equilibrium. The Fermi level μ and temperature T are well-defined constants for a solid-state device in thermodynamic equilibrium situation, such as when it is sitting on the shelf doing nothing. When the device is brought out of equilibrium and put into use, then strictly speaking the Fermi level and temperature are no longer well defined. Fortunately, it is often possible to define a quasi-Fermi level and quasi-temperature for a given location that accurately describe the occupation of states in terms of a thermal distribution. The device is said to be in quasi-equilibrium when and where such a description is possible. The quasi-equilibrium approach allows one to build a simple picture of some non-equilibrium effects as the electrical conductivity of a piece of metal or its thermal conductivity. The quasi-μ and quasi-T can vary in any non-equilibrium situation, such as if the system contains a chemical imbalance, if the system is exposed to changing electromagnetic fields, under illumination from a light source with a different temperature, such as the sun, when the temperature is not constant within the device, when the device has been altered, but has not had enough time to re-equilibrate. In some situations, such as immediately after a material experiences a high-energy laser pulse, The electron distribution cannot be described by any thermal distribution. One cannot define the quasi-Fermi level or quasi-temperature in this case. The electrons are simply said to be non-thermalized. In less dramatic situations, such as in a solar cell under constant illumination, a quasi-equilibrium description may be possible, but requiring the assignment of distinct values of mu and T to different bands. Even then, the values of mu and T may jump discontinuously across a material interface when a current is being driven, and be ill-defined at the interface itself. Technicalities. Terminology problems. The term Fermi level is mainly used in discussing the solid-state physics of electrons in semiconductors, and a precise usage of this term is necessary to describe band diagrams in devices comprising different materials with different levels of doping. In these contexts, however, one may also see Fermi level used imprecisely to refer to the band-referenced Fermi level μc, called Zeta above. It is common to see scientists and engineers refer to controlling, pinning, or tuning the Fermi level inside a conductor, when they are in fact describing changes in C due to doping or the field effect. In fact, thermodynamic equilibrium guarantees that the Fermi level in a conductor is always fixed to be exactly equal to the Fermi level of the electrodes. Only the band structure can be changed by doping or the field effect. A similar ambiguity exists between the terms chemical potential and electrochemical potential. It is also important to note that Fermi level is not necessarily the same thing as Fermi energy. In the wider context of quantum mechanics, the term Fermi energy usually refers to the maximum kinetic energy of a fermion in an idealized, non-interacting, disorder-free, zero-temperature Fermi gas. This concept is very theoretical. However, it finds some use in approximately describing white dwarfs, neutron stars, atomic nuclei, and electrons in a metal. On the other hand, in the fields of semiconductor physics and engineering, Fermi energy often is used to refer to the Fermi level described in this article. Fermi level referencing and the location of zero Fermi level, much like the choice of origin in a coordinate system. The 0 point of energy can be defined arbitrarily. Observable phenomena only depend on energy differences. When comparing distinct bodies, however, it is important that they all be consistent in the choice of the location of zero energy, or else nonsensical results will be obtained. It can therefore be helpful to explicitly name a common point to ensure that different components are in agreement. On the other hand, if a reference point is inherently ambiguous, it will instead cause more problems. A practical and well-justified choice of common point is a bulky, physical conductor, such as the electrical ground or earth. Such a conductor can be considered to be in a good thermodynamic equilibrium, and so its micro is well defined. It provides a reservoir of charge, so that large numbers of electrons may be added or removed without incurring charging effects. It also has the advantage of being accessible, so that the Fermi level of any other object can be measured simply with a voltmeter. Why it is not advisable to use the energy in vacuum as a reference zero in principle. One might consider using the state of a stationary electron in the vacuum as a reference point for energies. This approach is not advisable unless one is careful to define exactly where the vacuum is. The problem is that not all points in the vacuum are equivalent. At thermodynamic equilibrium, it is typical for electrical potential differences of order 1V to exist in the vacuum. The source of this vacuum potential variation is the variation in work function between the different conducting materials exposed to vacuum. Just outside a conductor, the electrostatic potential depends sensitively on the material, as well as which surface is selected. The parameter that gives the best approximation to universality is the Earth-referenced Fermi level suggested above. This also has the advantage that it can be measured with a voltmeter. Discrete charging effects in small systems in cases where the charging effects due to a single electron are non-negligible. The above definitions should be clarified. For example, consider a capacitor made of two identical parallel plates. If the capacitor is uncharged, the Fermi level is the same on both sides. So one might think that it should take no energy to move an electron from one plate to the other. But when the electron has been moved, the capacitor has become charged, so this does take a slight amount of energy. In a normal capacitor, this is negligible, but in a nanoscale capacitor it can be more important. In this case one must be precise about the thermodynamic definition of the chemical potential as well as the state of the device. Is it electrically isolated, or is it connected to an electrode? When the body is able to exchange electrons and energy with an electrode, it is described by the grand canonical ensemble. The value of chemical potential μ can be said to be fixed by the electrode, and the number of electrons N on the body may fluctuate. In this case, the chemical potential of a body is the infinitesimal amount of work needed to increase the average number of electrons by an infinitesimal amount, where F is the free energy function of the grand canonical ensemble. If the number of electrons in the body is fixed, then it is in the canonical ensemble. We can define a chemical potential, in this case literally as the work required to add one electron to a body that already has exactly n electrons, where F is the free energy function of the canonical ensemble, or alternatively as the work obtained by removing an electron from that body. These chemical potentials are not equivalent micro, except in the thermodynamic limit. The distinction is important in small systems such as those showing Coulomb blockade. The parameter micro remains exactly related to the voltmeter voltage, even in small systems. To be precise, then, the Fermi level is defined not by a deterministic charging event by one electron charge, but rather a statistical charging event by an infinitesimal fraction of an electron.